Welcome to another exciting Java class. Very excited. I was browsing on your homework there, trying to sort of see if I could understand what was going on. And as I went through and proceeded to take the standard deviation of the red plane, I saw there was a distinct separation between noise and signal. So in your homeworks, you were to create a window, a 32 by 32 window, compute the standard deviation of the pixels within that window, and then print them out. What we did was a hand segmentation of the noise and the signal. In the world of machine vision, or what is sometimes called computer vision, they call that the ground truth. The ground truth is defined as that area of the image which is said to be segmented correctly and is given to the program for training. And what you're doing when you attempt to extract the feature data of the standard deviation is you attempt to use that feature, the standard deviation feature, in order to be able to determine which segment is which. That is, to tell the difference between noise in an image and non-noise. And so you have taken a first step toward computer vision. How exciting. Isn't that exciting? Yes. Yes, Professor Lyon. Very exciting. Oh, not at all exciting. Okay. I feel bad for you. So what we did was we started with this real medical image, right? And then we proceeded to segment it. Here is the noise. We open it up, and it turns out we've got an array out of bounds exception at runtime. I thought we were supposed to fix this. Oh, this is that set pixel thing. I see what's going on here. Is there a set pixel? Oh. What happened here? Set window. Yeah, let's comment that out. I just wrote that. There we go. Noise, open. Ah, there we are. So as we look at the output of the windowed standard deviation for our noise, we can say, aha, if this is what noise looks like, anything with a standard deviation of 1.7 or less is going to be considered noise. Anything greater than that perhaps is not noise. Does that sound like it satisfies some criterion for segmentation? So if that's the case, then I should be able to say, aha, here's the 1.7, and I'll put it into a little conditional, as I have done, and if WSD, this is the windowed standard deviation, is less than that wacky looking number, I guess we could probably round that up to like 1.8, we print out, aha, I found noise. And in fact, for every window, since we started with a noisy knee, the noisy knee, it's all noise. And so everything is noise. So now let's try it with the signal. Right? So if it's not less than 1.8, it won't print found noise. And sure enough, it did not print found noise. So now if we go back to the original image, which was the knee image, which contains both noise and signal, we should be able to get a mix of things which are said to be both signal and then noise. So let's have a looky-loo. And what do we see? Aha, there's some noise. This is not noise. So then I see found noise, not noise. Noise, not noise, noise, not noise. And so there's a mix of windowed segments which consist of both how many windows? 10? I got 100 windows. How come I got 100 windows? It says here 100. Let's find out why. We'll start by oh, I think we printed out the width and the height. So let's just do that real quick. Make sure I got that right. So we'll start out with the knee, hit open, and now we'll go back to the top, and it says here the width was 320 and the height was 320, and the size of the window was 32 by 32. So what that meant to me was we would have 10 across and then 10 down, and 10 by 10 is 100. So I'm thinking 100 is a correct number of standard deviation computations. What do you think of that? Okay, I mean that's fair. I mean I could change the number of pixels in a window. If I did that, I might actually test this program for its robustness. But before I do that, I would like to know, is 100 windows enough? Is a 32 by 32 window measurement sufficient? What if I take the segmentation to the next level and say, look, if you find that it's noise, we'll paint it white, and otherwise we leave it alone. That's fair, and that way we'll be able to see right away what the program considers to be noise. And so this becomes a way to visualize the background noise as judged or interpreted by our, I'll call it, naive little segmentation program, which does nothing but compare the standard deviation underneath a window. So what I did, for better or worse, was I made get the window deviation a subroutine, which I then invoke, and then I said, aha, if the window standard deviation is less than my criteria, we'll set the window, and maybe we'll set it using some sort of a loop, right? So here's the window. My original short image beam gets set, and then we'll set it to 255, 255, 255. Said that too fast, but there it is. Now, you could say to me, but gee, Professor Lyon, what happens if you go beyond... Oh, do I need the standard deviation now? I shouldn't need that, right? I'm just doing a set. I just wrote this code, so obviously it's got a bug. So now we'll just try it and see if there are any array out-of-bounds exceptions at runtime. Now, one thing you can do when you're guarding your access to an array index is you can check the array index to see if it exceeds the length of the array in any particular dimension, that is, width or height. So if you run the program and you find it throws some sort of an exception at runtime because of an array out of bounds exception, oh, actually it doesn't. Oh, it doesn't. Oh, it's fine. What you can do is you can guard the input by saying, for example, oh, actually I kind of do that already. If YC is greater than the length, then break, which means stop accessing the array. If RC.length is exceeded by the index that you're attempting to access it by, then stop accessing the array. Break out of the for loop. Just stop whatever it is you're doing. Otherwise, you can continue. So break just breaks to the outermost for loop. It may iterate into another thing that's also out of bounds, but that's okay because it'll break out of that as well. And in fact, you could have combined these two conditionals and had a single break, and that might have been more elegant, but I claim this is more readable, and I prefer readability over elegance. So now we've got our little mechanism in place, which is going to set our short image beam. What I'll do to the short image beam is I'll get the image off the short image beam. So that'll take, what that does is it takes 3 two-dimensional arrays of red, green, and blue and makes an instance of a java.awt.image. And that Java AWT image can then be passed into imageutils.displayImage. So what I have done here is I've taken your homework, which estimates the feature of standard deviation in a small window, and then I've colored the image white wherever the standard deviation of the window in the red plane is less than 1.8. Is everybody sort of following along what I just did here? Does it bear repeating? I don't want to torture you with something that's obvious. Alright, so then what's it all look like? I have no idea. Aha! So, something's not quite right. Right? Little sort of bug in there. It did find noise where it shouldn't have done. Right? But it also found noise where it should have done. So that's kind of cool. We can sort of say it kind of worked, but it kind of didn't. So there are certain things about this that didn't quite work out. Now, what could we do in our little system for finding the ground truth with finer resolution? Is it the resolution, the window size? And if it is, should I take the window size and cut it in half? And if I do, what could possibly go wrong? Oh, let me count the ways. We'll just throw it in there for no particularly good reason. Aha! So now I've got a much finer grained window, much smaller window. Now there's 400 little windows being computed. That's kind of cool, right? And now suppose I do it again. Oh, I'm so psyched. Let's try it with 8 by 8. We're getting there, right? An 8 by 8 standard deviation. Now I'm thinking the standard deviation number has to be adjusted because we initially got the ground truth from a 32 by 32 window. But now we're in an 8 by 8 mode. And now we could see, aha, he's found a lot of signal which he colored as noise. But what if you were to take a look at what he's finding and classifying as noise? Maybe noise is something that we should try and identify with a signal. So if I throw the signal in there, he doesn't find any noise. So it turns out my ground truth might not have been so truthful. Right? This ground truth was a little bit too, I'll say, cooperative. Maybe there's a part of the ground truth that needed to be identified a little bit more clearly. What do you think of that? So suppose we said, okay, let's take that signal number and reduce it somewhat. Let's bring it down by 1.4. Aha! So it left a whole bunch of the signal alone. Isn't that interesting? What if we went down to 1? Whoops, I guess I just looked at the signal. So now it's kind of looking like a different matter, right? I mean, this is really looking different to me. So what's happened here is I haven't been able to clearly identify the signal, nor have I been able to clearly identify the noise. Neither has seemed to work very well for us. So what can we do about that? Any ideas? got nothing, huh? Well, how about if you just guess at something? Yes, sir. You mean something other than white? If I color it blue, it's not going to... Oh, you're going to find in grayscale images, red, green, and blue are identical. They're identical. So that won't matter. But one thing you could do, if you like, is you could color reduce the image. Or you could histogram equalize the image. Now, we've histogram equalized before. Let's see if I can get this to work. It should be ip.gui.main. There we go. Right, so here's my image. Now we'll get the histogram panel. And now we'll do the histogram equalization. Now, isn't that interesting? Now, if you were to use the histogram equalized image and then proceed to do the training by creating the ground truth, do you think you would get a different answer? Any ideas? Would it make a difference? You don't know. This is why image processing is a bit of an art. I don't know that anyone would know right offhand, but I would say probably not, because the texture really hasn't changed. All you've done is emphasized its brightness. Also, can you tell me, please, how I was able to do this histogram equalization? How does that work? Yes, it's homogeneous point processing. That is exactly right. Top of the class. But now, can you tell me how you implement that homogeneous point processing as it was described in Chapter 4 of the book? In other words, I'm asking, is there any learning going on here? I'm only asking a question. I didn't mean to be as facetious as that may have sounded.
So is there any learning?
Yes. I'll ask you the question I asked the rest of the class. Can you please characterize for me the procedure for doing the homogeneous point processing known as uniform non-adaptive histogram equalization? This is what you get for coming in late. Oh no, you don't have to be sorry. You can just answer the question. You can be truthful on this. Did you honestly now read the book?
I mean, I looked through it.
I looked at the book? Aha. Did you look at the book like this? You say, aha, it's a book. See, I looked at the book. Or did you look at the book like this? Make the guttural sound, and then you looked at the... Oh, there's words here. Oh. No? You read it. Oh, very good. So when you read the book, did you get anything out of it? Sounds like an interesting class. Be good a class for you to take, right? I'm going to stop torturing you now. I'm having too much fun at your expense. I'm sorry. So the bird's eye lowdown on this caper is you use a lookup table. And the lookup table takes input intensities and maps them to other output intensities in order to change the appearance of the image. So the tricky bit is how do you form the tricky question is how do you form the lookup table for doing a non-adaptive histogram equalization? And yes, it's in the book. It's even in the wiki. You can like wiki it. If you had Google, you could Google it. Google it. Well, the answer is you create a lookup table which has the shape of the cumulative mass function of the input image. Oh, that doesn't help us because we don't know what the cumulative mass function is. Tell me this. Does anybody know what the cumulative mass function is? No. Does anybody know what the probability mass function is? Yes? Go ahead, Brian. Let us know.
Oh, I can't put it into words.
Oh, dear. Probability distribution function. How about that? Can you tell us what that is?
Is that where everything adds up to 1?
Yes. All probabilities add to 1. Very good. Excellent. For example, there you go. It's the number of occurrences of a specific value in an event for your random variable. So your random variable in this case is going to be a pixel value. And the number of times a specific pixel intensity has occurred is something which you can count. And the way you do that is you use the pixel intensity as an argument to an array. And since the number of pixel intensities is finite because it's a digital image, you can usually allocate some space for that array. In fact, if it's a grayscale image, the number of pixel intensities is generally 256. So if you have an array which is 256 elements long and you encounter an intensity, give me a number, 75, right? A number between 0 and 255. You can take array element number 75 and increment it, thus counting the event of a pixel intensity value 75 as being a 1, because you encountered one pixel with that intensity. Then you get another pixel, let's say with intensity 75, and you go to array element 75 and you increment it again. And then you go and encounter another pixel, right, with intensity value 75, and you go to array element 75 and then you increment it again. Right? So now you have an image perhaps with 3 pixels, all valued at 75, and that's it. So now what you do is you say that the probability that you're going to encounter a pixel with value 75 is equal to 1, because that's the only kind of pixel you've ever seen. But if there were 2 kinds of pixels and there were 3 of them, let's say there was a 75 pixel and there were 3 of those, and there was another pixel, let's call it 150, and there were 3 of those, then you would say, aha, there's been a total of 6 pixels encountered, so you would divide the 3 that you counted by 6 and you get 0.5, and you divide the other 3 that you encountered by 6, total number of events, and you get 0.5, and now you have 2 probabilities which would sum to 1. And the probability of you encountering an image intensity of 75 would be about equal to the probability of you encountering a pixel with value 150, based on your empirical statistical analysis of the intensity of the pixels in the image. Does it make sense? It's seeming not to make sense. Didn't we do this already? I could have sworn we had this. Oh, PowerPoint has detected your graphics card is not configured. Really? I don't care. Leave me alone. So, somewhere in here. There it is. So here's your probability mass function, which is just like a probability distribution function with a difference. And the difference is there aren't continuous probabilities. And the probability mass function is ideally suited for the discrete structure of a random variable like a pixel. So somebody counted up all the zeros in the image and said there were 32. Then they counted up all the value 128s in the image and they said there were 16 of them. And then they figured out there were 16 255s, and there was a grand total of 64 pixels. So to get the probability mass function, you divide it through the total number of events that you encountered into the number of events for each one of the values. Thus, the random variable of pixel intensity was characterized by its probability mass function. Add up the probability mass function elements as a function of value, and you then create the cumulative mass function. And the cumulative mass function is nothing more than the running total of the probability mass function. That cumulative mass function becomes your model for your new lookup table. So what you do is you then create a lookup table that has the same shape as the cumulative mass function. That creates your histogram equalization. That spreads your pixels out so that they have a more uniform probability and improves your contrast. So we now know the difference between a probability mass function and a probability distribution function. Probability mass function is discrete. Probability distribution function is continuous. When you want to do a cumulative distribution function, you use an integral. When you want to do a cumulative mass function, you use a sigma. Right? You do a summation. So as a result, one is really very good for calculus, and the other one is really very good for for loops. Because for loops are used typically for adding up individual discrete numbers held in an array, such as the probability mass function. And that be that. You guys got it now? I've got that expression from Brian. You want to ask your question, Brian? Instead of making faces in the back of the class?
Yeah, okay. So the probability mass function and the cumulative mass function are just the discrete form of the continuous form and the density. See what I'm saying? Density.
The probability density function is continuous. The probability mass function is discrete. The cumulative distribution function, or cumulative density function? Yeah, I call it distribution. Maybe it is density. I've always called it distribution. Yeah, it is distribution. The cumulative distribution function is continuous, and the cumulative mass function is discrete. So when you're dealing with image processing that includes images that have been digitized, then you must be using cumulative mass functions and probability mass functions. That's for digitized data. That's discrete data. So now I can go through and create a little histogram computation here. And what's going on? The histogram array is accessing the image. This is a mask that only takes the least significant 8 bits, and then once that intensity is used to access the histogram array, it gets incremented. So what is it doing? It's counting the number of intensities that it encounters. So all I need to do when I find an intensity is say, aha, I found an intensity. Let's go tell the histogram array and increment that. Then we'll go through and create a lookup table based on the total number of pixels in the image. So now what we do is normalize the probability mass function array so that it ranges between 0 and 256. Once that occurs, I get my new histogram array, and that can serve as my lookup table. And this is what happens when you look at the histogram API. And that's it. That's a non-adaptive histogram equalization, also known as a homogeneous point process, which is exactly what Kyle had said. Okay, so what are homogeneous point processes? Man, Making my head hurt. I know what homogenized milk is, right? What's homogenized milk? That's the milk where the fat doesn't float to the top because they mixed it up real good. Right? So homogenized means all the same. That is even distribution. So homogenized milk has been made so that all of the globule distributions are the same throughout the material. Right? So you can sit there until you're blue in the face and your milk will not separate until it turns sour, at which point you will probably get some separation. You'll have curds and whey or something. That's how they make cheese, you know. They add a souring agent to boiling milk, and then the curds float to the top, and then you strain them off and put them through the cheesecloth, and you wind it together, and that's your paneer in Indian food. Oh, yeah. No, you need it. It's good, actually. Yeah, you can add any souring agent, lemon juice or vinegar, and then you knead it together after you put it into the cheesecloth, and then you flavor it with. It's like cottage cheese. It's farmer's cheese. It's how they used to make cheese. Yes. It's not McDonald's. Didn't they have exotic cultural foods where you went in Ireland, like haggis and things? No, you didn't eat that.
Pie.
They had pie, regular pie.
Yeah.
Yes. Okay. You did study abroad, right? Yeah, Ireland. Ireland is like a different country almost. Boy. You weren't in the country. Okay. Okay. So now we've got our histogram. Let's see what happens when we look at it after we equalize it. So we'll apply the histogram equalization, and then what we'll do is we'll bring up the little where is the window that shows the histogram panel? There it is. Now we'll show the histogram again, and we see, aha, the probability mass function has changed in a material way. Right? What has it done? It's spread out. Hasn't it? Right? And there are certain values, core values, which we could isolate after the histogram equalization, and others which we could remove. Suppose we did something like that with just plain old intensities. Would that make any sense? Well, there is a way to do this. We'll call it color reduction. Let's try the median cut algorithm. So what we'll do is we'll reduce it so that only a certain number of intensities are available. That's 256 intensities, 128, 64, 32, 16, 8. Now it's beginning to look a little bit more like we only have a segmented image. Suppose we revert now to our original image, and use our median cut algorithm. Well, what can we say about that? It didn't really help us very much. I can kind of see if I were to apply the image and then do a histogram equalization, the signal and the noise seem to make themselves evident pretty well. They're single pixel noise. That also, single pixel noise, we have individual white pixels, we have individual black pixels, and they're isolated pixels. This kind of noise has a very special name. It's called salt and pepper noise, or shot noise. So individual pixels, that is, pixels that are isolated all by themselves, they can be removed. They could be moved using a image processing technique known as median filtering. Median filtering. Well, now let's see. What's a median? That's another statistical thing, right? You know what the mean is, right? The mean, that's the average. Gesundheit. I got tissues here. You need a tissue? Okay. I even have used ones if you want to try and save and be green. There's a median filter, and what it does is it takes. Does anybody? I asked this question before. Does anybody know what median stands for? What it means? What's that? Your median salary. When you go for a job, what salary is that? That's the middle. So why is that good? Because somebody is making $20,000 a year working at Mickey D's, and someone else who's probably the CEO is making $1 million a year. And you need to know the median salary because it's meaningless, right? I mean, it's like $500,000 or something. So you're not going to get the median, not in that organization, because it's the middle. I'm not sure why people like to quote the median so much, but that's what it means.
Well, what about for a given position, like software? So they have like a median salary for a software developer, and then it's a bigger picture like McDonald's as the corporation is obviously minimum wage for CEOs.
Okay, fair enough. So if I had an array of points and they all contained, let's assume I had an array of numbers. Right? 1, 2, 3, 4, 5, 6, 7. Right? What's the median? 1, 2, 3, 4, 5, 6, 7. Yeah, it's like the middle, 3. But before you got it, suppose I said to you, well, the median is 7, 6, 5, 4, 3, 2, 1. Now what's the median? Maybe it's 4. Okay. Usually it's always the middle. So if it's an odd number of things, the median shouldn't really be changing. So let's just make sure I've got this right. I will use Notepad so we can see this. Otherwise, I would have done this on the board. So here's 1, 2, 3, 4, 5, 6, 7. Whoops! I got to put a little space in here. So isn't the middle 4? Isn't that the middle? When you have an odd number of things, you can find the middle. If you have an even number of things, the middle is not so obvious. It's like the average between two numbers on either side of the middle. Right? So now, suppose I said to you, aha, 7, 6, 5, 4, 3, 2, 1. What's the median? It's 4, right? Didn't change. Okay. Now let's assume I said that the sequence of numbers was 2, 3, 5, 6, 7, 1. Let's see, 1, 2, 3, and 4. So now I gave you a different sequence of numbers. Aha! What's the median? It's still 4. But wait, how did you get that? You had to sort it. You sorted it in ascending order, and then you found the middle. Ah, very interesting. So intuitively, you used an algorithm that said, step number 1, sort the list of numbers. Aha. Step number 2, report the middle. And then that report of the middle, that's the median. Good, right? And that's how you do it. That's exactly what you do. So now if I gave you a arbitrary one-dimensional array, you could find the median. Right? You sort the numbers, give me the middle, that's the median. Easy, right? Cake. So let's assume that someone has done this already. That's a fairly safe assumption. Where would they have put such an algorithm? Such an important mathematical algorithm? In the math package. Oh, I hear someone say, yes, yes, yes. And then there's this thing here called Mat1, and somebody will probably tell me that it's called Get Median, I hope. And there it is. There's the median. So now we can open this up and have a looky-loo and see what it does. And it says, aha, first sort the array, then get the middle. And that's the median, which is just what we said. Right? And then Mat1 sort obviously must sort this array, and what does it do? It uses a quick sort. Yeah, why not? And after it's done with its quick sort, it returns the sorted array. And that's it. And that's the median. So if we're real interested in knowing how this wondrous algorithm works, let's start with an integer array. Perhaps we could call it I. And then what we'll do is 1, 2, 3, 4, 5, 6, and 7. That sounds good. And then what we'll do is we'll call get median. Control J, enter. Quote median equals end quote plus get median. Get median of I. So that sounds simple enough. Let's see if this works. I hope this works. It really should work. Yes, the median is 4. Now suppose we go back to our little example in here and we say, aha, let's scramble it all up and give it different the numbers in a different order. Right? So let's see now. I think it was something like 6, 4, 2, 3, 1, 5, 7. Right? So that has 1, 2, 3, 4, 5, 6, and 7 in it. So that should work. Just the same. The median is 4. Just what you'd expect. Good deal. Right? So what does this have to do with image processing? Aha. Glad you asked me that. So what we'd like to do is get a median filter based on a window that travels across the image and then proceeds to report the median value underneath that window and create a new image. And my claim is that this will remove shot noise. So first thing we'd like to do is, I think, see if there's some way that we can create some shot noise in an image. I think that's a fair question. So how do you create shot noise in an image? Well, image utils dot get image, and I believe you can put in an arbitrary width and height. So we'll put in a number. How about we do something like 512 by 512, n paren, Image Utils says he's unhappy. Enter alt. Enter. Import class. Get an image. Here's an image. Whoops. Image. Whoops. Haha. Image. img equals. And now he's going to ask me to do the same thing with the import. And now I should be able to, that'll probably be a black image, but I want to do something to it. So let's do this. Image utils dot. Now, do we have shot noise here? Get shot sh. No. Salt, perhaps salt and pepper. sa. No, we don't have it. Really? We'll have to write our own salt and pepper algorithm. Unless it's already done. We could do a quick search. It's in the book. It must be done already. Does anybody have a book? Yeah, I know. You want to look at it? While I'm doing this, find and path. Just use the index. Salt and pepper. I think it's salt and pepper. Shot noise. It's got to be in there. Yeah. I got a whole bunch of it. Yeah, it's in there already. There's even some filters. Salt and pepper processor. It's a processor. Ah, okay. Fair enough. Salt and pepper processor. So, we'll make a new instance of a salt and pepper processor. Salt, S-A-L-T, and pepper processor. Yes, S, I guess I can do this, equals new salt and pepper processor. And now, what does that do for me? Dot process, get number of sprinkles, set number of sprinkles. Oh, that sounds good. Let's make a lot of sprinkles. Here's 1,000 sprinkles, 10,000 sprinkles, n paren sen. And now what we'll do is we'll go to the salt and pepper processor and we'll process the image and make a sprinkly image. And then what we'll do, what shall we do? Oh, I think this is going to return a new image, so we'll just overwrite the old one. And then image utils dot display image, put in the image, and here's the salty image. And that's all she wrote. I guess I can comment out this other stuff about the median. And now I have a salty image. Is there a question? I thought I saw a hand. Oh, look! It's a salty image. I beg your pardon? It's outer space? It's outer space. Outy space. Well, it's got the shot noise in it. The question of whether or not there are is salt and pepper in the image, because it's a salt and pepper processor, is not immediately clear. So what we'll have to do is we'll have to get our image from someplace. So why don't we get our image from a real image? We'll call it futil.getFile, and we'll select and an image. What is the problem here? Is it futils? Oh, I've spelt it wrong. F-U-T. Futil. I've got issues with my spelling. Now what's your problem? Import class. Get read file. Read file. Now what's your problem? Oh, he's good. So let's run and see where we are. Might as well start with the knee, since that's what we were working on. Oh, very nice. Let's try it in color. What shall we colorize? Could colorize Dr. Diffracto. Ooh, that's a scary one. So, as it happens, Dr. Diffracto has been covered with salt and pepper noise, shot noise, 10,000 little spots all over the place. And now we have a basic underlying understanding of median and how to invoke the median filter. We also know a little bit about windowed processing. So now we can have a median processor run through a window, give us the median value underneath the window, and replace that in the original image. How exciting. Yes, sir.
Can you go over how you set, like how you move your for loop?
Oh, in the for loop?
Because I just have 10 windows. I had 100, I think, and I thought that was too many. So I changed something.
Oh.
And now I only have 10, which is awesome.
Well, what you want to do is if you have a doubly nested for loop, you want to have that doubly nested for loop iterate through every one of the pixels in your image, but it should iterate through those pixels in steps of window size. So if the window size was 1, it would visit every single pixel. If the window size was 2, it would visit every other pixel. And then within that pixel at the upper left corner, you would create a window which is 2 by 2, and you would do your processing inside of that window, and then you would proceed to take the window and move it to the next 2 pixels over. I don't know if I explained that right. Yes, it's quadruply nested. The way I wrote it here, if you look at the statistics window, what I did was I said, you know, here's your window, here's your doubly nested for loop, and then inside of the doubly nested for loop, we will get the window standard deviation, and then we will set the window. Each one of these is in turn doubly nested for loops. So they are implicitly quadruply nested. Now the way you can see that is if you go to the definition, Control B, you'll see, aha, when you get the window standard deviation, what's happening is you're starting at a location, and then you're going through that location. So here is what we're doing. XCYC is equal to the X plus the Y, the Y plus the Y size, that's the Y size of the window, the X plus the X size of the window, and then we can proceed to identify the window value in that small area, and we get the standard deviation just of that little window. So presumably that little window is something that doesn't cover the entire image. It's a smaller, it's like the window is an image, but it's a small image. And what it's doing is you're populating this small image from the big image by taking the little window and moving it across the big image.
Is there a reason why you did rows against that? And then you switched Y and X? Because that's like the only difference between them, more or less.
I think it would work the same the other way. I'm going, in this case, it's going column major. I suppose I could flip it around. It wouldn't matter. From a computational point of view, I should think you would get the same result. Although, if it starts throwing array out of bounds exceptions at runtime, I'd take it back. I'm not really excited at the prospect of making that change right now because it's a little distracting. And besides, I have working. Yeah, I have working code.
I have my thing at the
Oh,
moment.
okay.
My print receipt.
So you have some sort of bug, right? It's a simple bug. So at the end of the day, we wanted to come back to this idea that you would have a window moving across the image, taking the median computation inside of the window, and then returning a value. Now, I wonder if there isn't a way to get the median in a small two-dimensional array, such as a window, because that would be convenient. And there isn't. Although we could have done that, there isn't. Oh, here's median. That's the median of a vector. I don't see... Here's print median for a two-dimensional array. How could that possibly work? Let's find out. Let's see. So if I take a two-dimensional array, what is this doing? Oh, this is Java code, which is actually writing Java code. How fun is that? It's writing out public void, and then it writes out the actual array. That just sounds like fun. But somebody somewhere is calling median on images, and I think we can find a place to do that if we go to j2d.gui.main, j2d.gui.main, and we run our little program here. We should be able to open let's open this. Here's an image. We should be able to process it with shot noise. If I could find the shot noise. I'm having a little trouble finding the shot noise. I got too many menu items here. Well, it's got to be in here. Here, salt and pepper 100. It's there. 1000. Oh, that's shot noise. So now we can apply the filter, and now what we'll do is we'll try and get the median the median filter done. So we'll go to what's called morphological filter, and we'll get the middle, which is the median, and we'll use a square and see how that looks. Wow, that changed things quite a bit. Let's try this again. Filter, morphological filter, middle. Let's try horizontal. And that didn't work out so good. Try it again. Filter, cross. You know, I think it may be the case that it's modified the image prior to my no, it's fine. Apply, filter, median. Oh, here are the median filters. I was using middle. Here's a 3x3 median filter. That sounds promising. There. It got rid of a whole bunch of the shot noise. Let's apply that. Let's try it again. Filter, median. Let's try 020 pels after first non-zero pel. Oh, that sounds right. Show median filter buttons. Let's try a bunch of buttons. We'll just try a few different things and see what works. Ah, that was very good. Made it a little blurry, but it got rid of the shot noise. So median cross 5 by 5. Good deal. So now let's see what it does to the knee. Open, and here's the knee. And then what we'll do is run the histogram panel, apply the image, and try some median filters. It's making things a little blurry. A little blurry. Very blurry. Now, what did we do to get the individual shot noise from before? I think that was a color quantization with a median cut algorithm, which is kind of cool, because it's a different algorithm, really. Then we apply that, and now we run our median filter and see what happens. Oh, that's bad. So, sometimes I think what happens in image processing is you got to try things. And after you try a few different things, you say, geez, these algorithms do more harm than good. And you have to move on to other things. Yes, sir?
You didn't try the cross 5 by 5.
I didn't? It ain't doing me any good. No good at all. That's not too bad, actually. Maybe if I invert the image it'll work a little better, but at this point things are getting kind of wacky. Nope, it ain't working. So the knee is looking lousy. We haven't been able to identify the background and the foreground yet. We need better features. That's my conclusion. What do you think? Yes. I think so. And we covered a lot of interesting and wonderful image processing algorithms today. Right? What did we look at? A lot of interesting advanced color image processing algorithms, right? Where there was color reduction, which is known as requantization, also known as the median cut algorithm. That's what we used. Then we used a sorting algorithm and found the middle, and we call that the median algorithm. Right? And the median algorithm was different from the median cut algorithm because the median cut algorithm was working in color space. But the median algorithm that we used was just working in absolute pixel values. So that's interesting too. So I think what we've done here is we've gone through several interesting and wonderful chapters in the book. If you looked at, let's say, the median cut algorithm, you'd be in the color image processing section. In the color reduction section, I think is chapter 13. If you looked at the median algorithm, which is similar but a different algorithm with different application, you're looking at morphological image processing, which is chapter 12. And so what I thought I'd do in trying to do this little image processing is not restrict myself to going through the chapters sequentially, but jump around a little bit so you can see the richness and vastness of the different operations which you can perform in order to enhance an image. In other words, let's see if we can motivate some of the later chapters that are coming. What do you think of that? enthusiastic response here.
Just give us a very hard homework problem.
Huh? I should give you a hard homework problem? Why is this happening? So we talked before about some homogeneous point processing in Chapter 4. We talked about the eye and how it is a camera that effectively gives us a finite bandwidth into our brain. Would somebody mind doing the door for me? We talked a little bit about the issues that have to do with the iris and how it's like an f-stop in a camera, emitting smaller and smaller amounts of light, but making it sharper. So there's a basic engineering trade-off. When we have less light coming into the eye in a bright room, we're able to see with better acuity because we are reducing what's called the ray bundle. Right? The ray bundle diameter, the more it's reduced, the smaller the circle of confusion that occurs optically. And so, from a geometric optic point of view, it's very nice if we can get the ray bundle to go through a very small area. But we only do that when our pixels, when our pupils get very small, and that only occurs when we have a bright room. We talked a little bit about the bandwidth that goes through our optic nerve as a result of what's known as the synaptic retention time, which is then multiplied by the total number of neurons in our optic nerve. That nerve bundle feeds into a short-term visual memory known as the visual cortex. The visual cortex stores, like a frame store, the entire image. From that frame store, we're able to extract features, and those features are used to create what's known as a saliency map. That is, features of interest. Saliency means relevant. So we have these response curves to different electromagnetic radiation emissions, and they are Gaussian in their shape, and this leads to what's known as biologically motivated image processing. That is, we like to see things in a certain way that's similar to the way our eyes see them, and so we do the image processing in a way that's similar to the way the eyes do its image acquisition. We already know something about digitization. It requires that we requantize random variables so that they have a finite number of different values, and we also know that the finite number of different values can give us a finite number of bits that's used to represent those different values. And so if we efficiently pack those values into a binary word, we take the log to the base 2 of the total number of different numbers. So taking the log to the base 2, for example, of 255 gives us a number like 8, or maybe it's 256. So that means 2 to the 8 is going to be 256. And so what that says is there are 8 bits which are used to efficiently represent the 256 different possible values. If we use the least significant bit as a means of determining the quantization noise, then we can obtain a signal-to-noise ratio. And typically that works out to be about 6 dB per bit. Add an extra 4.8 dB. And the way that works comes about from the laws of logarithms, which you can see here. What can we say about signal-to-noise ratio that hasn't already been said? Why do they use logs when they talk about signal-to-noise ratio? Because when they're dealing with bits, it's implicit that the bits the number of bits is logarithmic in the total number of values, right? That's how you get the number of bits. Take the log of the total number of values. Why do they use dB in decibels? That's a good question. I know about the log, and dB has log in it, And in communication systems in general, I find dB is used all over the place. But why should dB be used in communication systems? Why? Because you can start with a transmitter. Think about how much power you have. Kilowatts, right? I used to be chief engineer at a radio station. We had a 10 kilowatt effective radiated power. Kilowatts. And how much power did you get from the antenna at your little FM radio? You'd be lucky if you got milliwatts. Right? So you were many orders of magnitude away. You were 6 orders of magnitude away from the transmitted power versus the received power. So using logs makes perfect sense when you start to talk about the actual signal amplitude as it's received by the antenna. It's suppressed by 60 dB or 100 dB, and those numbers in decibels actually represent very large quantities, kind of like the Richter scale, right? The difference between a 7 and let's say an 8 or a 10 is like the big one. I don't think we've ever had a 10 on this planet, but we've had a 9, and that was in Japan. And then it was a tsunami. It was a big deal that came afterwards, right? Because it was a big shift. And then that tsunami didn't just hit Japan, it went across the ocean and hit California. And it also hit Hawaii. I mean, that's how big that was. A lot of energy was released.
So how does I guess analog for communication relate to biomedical?
Well, when we talk about dB, we're generally talking about a way to represent large differences in quantities with relatively small numbers. So when I say to you that I have an analog system and the input is a microphone and the output is line level. Well, how did I get line level from a microphone? I must have put it through some sort of an amplifier which gave me gain. And how much gain do I get? Well, I describe it in dB. I say I had 40 dB of gain. Or I got a signal level out that's plus 8 dB, but what went in was, let's say, minus 55 dB. And usually they describe it as a voltage into a specific load. So many ohms, and they do it in power. But when you're looking at something that goes from, let's say, minus 55 dB to plus 8 line level, then what you're really seeing is an enormous voltage gain, right? Because it's going from millivolts to, 1 volt peak to peak or something. This is not coming out clearly, but this says RMS. I don't know why it doesn't look nice. Is there a way to make that look nice? Is it the background or something? Format picture? How does one change the background? Do you guys know about these things? No fill. Solid fill. That makes it worse, doesn't it? No, it does nothing. I can make it larger. Yes, of course. It looks crummy. It just looks crummy. Doesn't it? It's supposed to be root mean square noise. That's what that's supposed to be. But it just looks so bad. So then we had this thing about traveling window analysis, and this is where we started to do standard deviation computation. Let's see now. You guys have had a signal processing course. What's the Kronecker delta function? Yeah.
Oh, isn't that just the discrete direct?
Yes, that is right. A Kronecker delta function is going to be exactly equal. First of all, Kronecker delta function is not a function. That's the first thing. Second thing is, it's an impulse that occurs with unit area at exactly time 0. And it has an infinitesimal duration. So it's a mathematical abstraction. When you sample an input signal, you're essentially multiplying it by a series of Kronecker delta functions. You're taking a switch and you're sampling and holding the input signal until the next time that you flip the switch. And so that is part of how you model the sampling function. You use a Kronecker delta function pulse train. So here it is. Sampling an image is done with some typical frequency, and we already know about the Nyquist theorem that says that the maximum frequency that you want to be able to digitize has to be sampled at twice that frequency. So if you want to sample something at 100 hertz, then in general you can't detect anything beyond 50 hertz at most. Well, when you do the sampling, what you're doing is a sequence of sample and holds over time, and that is represented as a convolution. And convolution is really nothing more than a sliding window dot product. Okay, let me stop myself right there. What's a dot product? Yes, I do know. So if I had two vectors and I wanted to take the dot product, and I knew their magnitude, vector A, and the magnitude of the other vector, vector B, and I knew the angle between them, how would I compute the dot product? Yes, the cosine of the angle between the vectors is multiplied by their magnitudes, the product of their magnitudes. Now, let's assume that you had digitized something so that you had two one-dimensional arrays, and you wanted to find the dot product. Let's assume the two arrays are the same length. Then what would you do? Let's say I've got two arrays that are 3 elements long. Array A has element number 1, 2, and 3, and array B has element number 1, 2, and 3. And now I ask you, can you please compute the dot product?
One by one.
Yeah, you multiply element 1 in A, or I'll call it A1, by B1, and you multiply A2 by B2, you multiply A3 by B3, and then you add up the products. Add them all up and you get a single scalar number. If it's a 1 by 3 times a 3 by 1, the answer will be a 1 by 1. Right? So you did a piecewise multiplication, and then you added it all up. That's what you did. So that's your sliding window dot product. The sliding window part, that's when the A matrix is much larger than the B matrix. Then what you do is you form the dot product between the B matrix and a submatrix in the A matrix, and then you go and you move the B matrix over by 1, and you do the dot product again. That's a sliding window dot product. So, in the first example, the A matrix was the same size as the B matrix, so you did a piecewise multiplication and you added up the product terms. In the second example, you couldn't do that because the A matrix is way bigger than the B matrix. So you took the submatrix of the A matrix, which is the same size as the B matrix, did your piecewise multiplication, added it all up, then you took the B matrix, you moved it over by 1 element, and did it again. And you moved it over by 1 element, did it again. That's what makes a sliding window dot product, because you're sliding the B matrix across the A matrix. And you're using the B matrix as an analysis matrix. And then the output goes into a new matrix. We'll call it the C matrix. What do you think of that? So with convolution, why am I telling you all this? With convolution, you're doing a sliding window dot product. That's all it is. In other words, you're taking it's actually a doubly nested for loop. You're taking one array of elements and you're multiplying it by another array of elements and adding up the result. And that's how you do it in the continuous domain. In the what shall we call it? The discrete domain, I think that's correct. You use summations, you use sigma instead of integrals. And when you represent this convolution, this sliding window dot product, you represent it with the funky looking asterisk. It's not a, how you put it, multiplication. It looks like a multiplication, but it's not. It's a special operator. Quantization is one of those things that can give us error. And in an image, when you have quantization error, you see it. And the reason you see it is because your eye is very sensitive to changes in gray level. So when you re-quantize an image by reducing the number of gray levels available, you create this modeling effect where you are actually seeing this distortion. So in the lower right corner we see the mandrel in a grayscale image. It's a continuous tone image, but it's really just 256 different quanta. And now in the upper left we see only 2 different quanta. And so it's very clear there has been some contrast improvement because the high levels are much higher in intensity than the low levels, but there's only 2 different levels, and as a result of that thresholding we have caused an interesting visible quantization error. Now the question then is, well, which image looks better? You might say, well, the lower right image looks washed out. The upper left image has no contrast. But maybe the lower left image looks very good. Right? Maybe. I don't know. Or maybe the upper right image looks very good. It's a perceptual thing. If I had histogram equalized it, I could have kept the total number of different numbers and spread them out to improve contrast. And of course monitors are made for people, and people only have a limited visual range. They can see from perhaps 400 nanometers out to 800 nanometers. After 800 nanometers it's infrared. Prior to 400 nanometers it's ultraviolet. And that is my shtick for chapter 5. Let's save the interesting things. And now we can get to the meat of the matter in convolution. But before we do, let's do a break. We'll do a break. I knew you were going to say that.